Okay, this website is a really good one just to kind of show you what we're doing. Basically, you're going to have a function and we're going to estimate it using a polynomial and its derivatives. Okay, so you all know what the cosine function looks like, right? Like that, correct? What we're going to do is use a polynomial. Okay, there's a first order polynomial, right? Does it match the curve very well? No, it doesn't. Okay. It's also centered at 0. Okay, so we are actually centering our polynomial at 0 here. There's x squared. Does that fit it? On some certain interval it might, right? Yeah. And we are going to get to the point where we can actually calculate the amount of error in different spots. It's called the Lagrange error bound. Okay. Now let's look at, now there's x to the 4th. Is that estimated even better? But look at x squared. You can kind of see some blue in here, all the way to the x-axis. X to the 4th matches all the way down into here. Okay, and then we can do x to the 6th. Is it better? 8th? Yeah. So it keeps getting better and better on these intervals. Okay. There's 12, 14, x to the 16th. Well, on the shown picture, there's the 22nd. Okay, what you're saying is, number one, are you ever gonna get to the end of cosine and have a perfect match? No, you're not. There's always going to be some spot where there's an error. Our goal is to estimate it so that the error is minimized, right? Or on certain intervals so that we have an exact match, because polynomials are pretty easy to work with. Okay. So do you notice a pattern in that polynomial? Okay, that's one good pattern to notice for cosine. What else do you notice? 2. Oh, yeah, go ahead, Hunter. Yeah, good pattern to notice. Okay, any others? 2, 4, 6, 8. Who do we appreciate? Polynomials! All right. Sorry, I had to throw that one in there. Okay, so you're seeing some patterns for cosine. Cosine will follow the same pattern every single time. Okay. Take a guess. What do you think sine might look like? Okay, so Hunter's guessing that the signs will be opposite. Alex thinks we're going to use odd exponents and factorials. Let's check. Woo! Alex saves the day again. Yeah, it goes with the odd exponents. There's a reason for that. There's a reason for that, and I'll show you why it happens. It has to do with the derivative of sine, which is cosine. We use cosine to develop this polynomial, ironically enough. And we use sine as well. We use derivatives. Okay, it has to do with the values of cosine at certain places. All right? Now, here, let me really wet your noodle. These were centered at 0, correct? What would happen if we center it at something different? So cosine, the original cosine that we looked at was 1 minus. Okay, it's going to change that. And we're going to have 7 pi over 4. See how it's moved it here? It's moved the approximation, right? It's centered it somewhere else. X minus 7 pi over 4 versus x minus 0. That's all that is. There should be an x minus 0 here, but there's not. Okay, so it's a little messier, but you can see that it still gets the job done. Okay. Here's e to the x. Right. Constant. There's a linear approximation. You've done linear approximations, right? Because you calculate the derivative, get the slope at that spot, write a line for the equation, for the tangent line. That's a first order Taylor polynomial, ladies and gentlemen. Yes. Yeah. It really is. I'll show you. I'll go over that one, but okay, there's x squared cubed. You see how it's getting better? Yeah, I know. We got a retarded polynomial over here. That's not politically correct. No, it's not. Here's the log x. Oh wait, I did the wrong thing there. No, I'm just kidding. Okay, but you see what Taylor polynomials are doing, right? Okay, good. So we're gonna mathematically figure out what those polynomials are today. Oh, come on. It should be fun because it's derivatives and they're easy. Right? Factorials is just one factorials you don't have to worry about.
How come we didn't know this 10 years ago?
So, the hard way. This is not possible if we know this. If we use derivatives today. Okay. Yes, I'm acting captain. Why did I have to run out of the room? Bad things happen. Okay, so. Oh. That's awful. Okay. It takes the computer a little ways to catch up with me because I'm so bad. Okay, that's why it goes e to the x, right? Some approximation. Calculate the equation of that tangent. What do you need to do? We need y at 1, right? Which is e to the first. And we need y prime at 1, which is also e to the first, correct? So what you end up with is y minus e equals e times x minus 1, correct? And if I move the e, I have a first degree Taylor polynomial.
So we've been doing this since
First degree Taylor polynomial centered where? X equals 1. this since last fall. You just didn't know what it was called. Oh, so sneaky. Right? Now I'm going to teach you how to extend that. Because what this basically is, this is, let me write it in a different color. Different color. This is y at 1, correct? Plus y prime at 1 times x minus 1, which is our this is our a. This is our center. So I could have put 0 in there, I could have put 2 and just square it. It just moves this equation. If I centered at 0, I would move it to here. Right? How would I tack on and make this a second order Taylor polynomial now? So if I wanted to get that.
So then would it be
Follow the pattern here.
the first one plus y at 2
Times. See how the pattern's developing.
what
So
the
you
heck
just
for
need-
Okay.
last one, those examples. So it's just going by derivative. So it go like, so the derivative is using the direct correlation to the power with like.
Yeah, those
like
match
x.
every time.
So-
These three items will always match.
Oh, so it really, okay, it really
Makes it real nice, right? Generalization purposes. So, let's generalize this. We're going to call it the Taylor polynomial, nth degree. It's a generalization, right? The Taylor polynomial, nth degree of some function of this. Let's say we are centered at x equals a. So in our case, there was 1, right? So this was, go ahead, Hunter. F at a. No. General polynomial centered at x equals a of f of x. Okay.
So then
What's next? F prime at a times x minus a.
would it be minus them?
You don't have to write this, but not a bad idea. But you see how it's a first derivative, first power, 1 factorial, right?
So then it would be minus, wouldn't it?
No. It's always plus. This right here is what determines the positive or negative. Right? I'll show you an example that'll clear that up. But these derivatives will determine whether it's positive or negative. But in the general formula, we just write plus. So you can kind of see the pattern. You're gonna have to sometimes you're gonna have to calculate 5 derivatives at their values and f at 5 values. it's all stuff you know, you're just plugging it into this formula. What is the nth term?
So f n degree a x minus a to the n
That's it. Yep. So if it's a fifth degree Taylor polynomial, how many derivatives are you going to have?
5.
Five. You're gonna have, how many terms are you going to have?
6.
6, because you have the constant.
This is the stuff that's clicking.
Okay, I can tell.
And like I'm actually enjoying this because having the blanks there.
What?
Coding time.
What? Okay.
The
Moving on.
Exclamation.
That thing.
Yeah. A Taylor polynomial at your book will use this language. I'm pretty sure the AP has gone away from it, but a Taylor polynomial centered at, it's just a different, it's called a Maclaurin polynomial. Maclaurin, not McLaren.
Dang it.
No sports cars in here. Okay. Your book will use that. I think that the AP people have just found a Taylor polynomial center.
Oh, yes.
So a Taylor polynomial centered at 0 is called a Maclaurin polynomial. So if you see calculate the Maclaurin polynomial for each x to the fifth degree, you know it's centered at 0, right? So what is calculate? Is cursive, Alex? You guys not learn that anymore?
Well, it's just like a.
No, all I do have to do is
Well,
text.
it's because the dot is real off of
Yeah.
the I, and so we're like,
That's really like.
or stop. It's like that one
It's a
thing.
smiley face now.
It's like that one.
Ah, take that.
No, it's a smiley face that's like, kill me.
So we'll use u dx to get the calculate the fourth degree of a Maclaurin polynomial for u dx. Again, it's always a wise idea to, every time you do this in the homework, write the formula. Is that a pain in the butt this time?
Yes.
So, what are we doing? The fourth degree, right? So we need f at 0. And you can,
Oh, we can write it like that?
Well, if we don't say to solve it, sure. Simplify this. No.
this is, right, this is jogging your memory, getting your memorization skills down, just writing these polynomials out, right? And it's really not that hard. All you have to remember is one term. The dx exponents. Well, two terms actually. Okay, so what is the t for x of u dx? Let's do this. We need f at 0, right, is 1, right? What's f prime at 0? 1. What's f double prime at 0?
It's forever one.
Yeah, because it's always e to the x, right? Stop writing.
Currently thought here.
What? So you'll have to calculate those values. Yep. Now here it's easy. When you get to like sine, it'll be sine x, and then you'll have cosine x on the next derivative. What's the next derivative? Negative sine, and then you'll have cosine. You have a lot of thinking to do, right? All right, so let's write this T4. 1 plus 1x over 1 factorial, right? This is x, this is 0 here. And then we have 1x squared over 2 factorial plus 1x cubed. You don't have to, no. I'm doing it so you see it. And you have your fourth retailer column. Center is 0. This is also called a chord. You might also be asked, calculate the first 5 terms of the polynomial.
Which is the fourth, right?
Yeah, 5 terms, correct. Okay, so this would be the same thing as first 5 terms. Okay.
But did they just change the terminology from the core?
The corin is just centered to 0. Formally. Good.
At least they haven't had to explain the detail.
Why?
See the derivatives getting pretty lengthy here. Yeah. So yeah, they get a little bit. So we need f at 3, correct? Woo! Step 1 is done.
Step
So
1.
that would be the first term, wouldn't it?
First term. Yeah. All right. What's f prime of x?
It's x plus 1 to the 1/2.
Okay. What's the second derivative?
X plus 1. It would be negative 1/2 here.
3 over 8. It'd be positive 3 over 8. Right. Now, are you starting to see something here? Signs are starting to alternate. And then after the fourth
Is negative 15. Minus 7x.
oh my. Right.
So then the factorials will just be like, they wouldn't be like 1/2 factorial, would they?
Now what's that prime of 3?
1/2
It's 1/4. Remember, this is in the bottom. It's the square root of x plus 1, but it's below, right? If you rewrite it, 1 over 2 root x plus 1. Yeah. What's f double prime at 3? Four cubed, 64. Square root is 8 times 4 is 32. Okay. What's 4 to the 5th? 256? No. Let's need a calculator now. 2, 4, 8. It's 4, 16, 64.
Oh.
Times 4 is 256, 10, 28. No, 10, 24. Times 8, or what's the square root of 10, 24? 32 times 8. 6.
Now that would be 4 to the 7th. The square root it, then times 16.
That makes sense.
It's to the 7th.
Oh.
Oh.
Remember 2048 out.
Okay. Now we can write our Taylor polynomial, right?
So,
2 plus 1/4 x minus 3. And what's the factorial? 1?
why is that x minus 3?
It's centered at 3.
Oh, so x equals, oh.
Okay. And then minus 1/32 x minus 3 squared 2 factorial.
Wait. Now, what are the numbers? Oh, never mind.
This is in front. This is f prime at a, it goes in front, and you have x minus a. A is 3 in this case, right? Because that's what everything we did is with a. First power, 1 factorial. Now we're doing the second. Second derivative at 3 is 1/32. X minus 3 squared, 2 factorial. Plus 3 256. X minus 3 cubed, 3 factorial. And minus 15, 2048. X minus 3 to the 4th, 4 factorial.
Hey, it wasn't a page.
Can you imagine the birthing pains of this one? It was not a page extender. You bet it is. 14 rounder. Any questions? You could probably reproduce this.
Hey, Lynn.
Oops.
No, we can't.
Are you down in your office?
So this is today.
Can you
Tomorrow.
open that middle door for the sanitary supply guys here?
Tomorrow we'll work on these
Yeah.
types of problems, and then the spiral is.
So that's.
So
that's
today you
an
can do
11.
these.
That's an 11.
This is a nothing.
Okay.
It's a scribble mark. It's not a number. Let's do Tuesday. So we'll finish a few more Taylors today, tomorrow, and
It always becomes.
first couple days are not equal. Well, you know, it's an inanimate object. It cannot become evil.
It can.
It can be used for evil, but it cannot be evil in of itself.
But in my mind, math is evil.
Math is not evil! It can be used for evil. Haven't you ever seen Despicable Me?
Yes.
Okay. My
It's
point is
evil.
proven by a cartoon.
It is evil.
Have a nice day.
Yes.
I just don't understand how